Now we're live.
Hello, my name is Andreas Geiger, and it's my great pleasure to introduce the 42nd Symposium of the German Association for Pattern Recognition with a special invited talk series today. Originally, we had planned to gather all together here in beautiful Tübingen and have some beer at the riverside or visit the castle of Hohenzollern. But as we all know, this is unfortunately not possible. And so we hope we can provide you still with the best possible experience of the same conference through this virtual event in the next couple of days. And of course, we hope we will see you in person at some point soon in Tübingen as well. Let me first briefly introduce the team, the organization team. This conference is organized by the general chairs, including me, Michael Krone, Hendrik Lensch, and Kai Niesel from the University of Tübingen, as well as a fantastic technical support team, including Andreas Engelhardt, who is leading the support team, Aditya, Tim Beckmann, Alexander Götz, and Jules Koyam. The AJM GCPR 2020 is organized by the program chairs, Zeynep Akata and myself from the University of Tübingen, as well as Thorsten Sattler from the Czech Technical University in Prague. And Thorsten and me are co-chairing this session today. I also want to greatly thank our sponsors and partners. Even though this is a virtual event, sponsors are necessary to finance it. And we're super happy to have Amazon as our gold sponsor, as well as Google and KAUST as our bronze and academic sponsors. And we have, again, as in previous years, Daimler, Cognex, MVTech, and VRVIS as the best paper and award sponsors. So this is an overview of the program. We are here on this Monday session, the special invited talk session that we are holding for the first time in reminiscence to the CVPR area chair workshops here at GCPR 2020 with a set of renowned experts in the area of computer vision and machine learning giving overviews over their latest research. So if you want to join, and I guess you do so already, if you watch this stream, go to our conference website, click on program, and you will see the program as well as these two short link buttons. You can follow all the sessions live on YouTube, and you can ask questions via Discord. So click on the Discord button. The Discord server will open. This is an invite link, and you will, for this session today, just navigate to the special invited talks channel where you can ask all your questions. Please ask questions anytime during the talk, and I will simply read them to the speaker after the talk in the Q&A session. So we have an exciting program today with several invited speakers, including Matthias Bethge, Sabine Süstrung, Vittoria Ferrari, but Banchile, Sio Tang, Christoph Lampert, and David Scaramuzza. Anna Koreva couldn't make it today because she's ill, so we have a longer break here in the middle and resume again at 4:30. The first session is chaired by me, and the second session will be chaired by Thorsten Sattler. So now, without further ado, I want to move forward with the first speaker for today. Matthias, can you please share your screen now? And I will introduce you in the meantime. It's my pleasure to introduce Matthias Bethge as the first speaker of our invited talk session. Matthias Bethge is a professor for computational neuroscience and machine learning at the University of Tübingen and a director of the Tübingen AI Center, which is a joint center between Tübingen University and the Max Planck Institute for Intelligent Systems that is part of the German AI strategy. He's also an Emerson Scholar and co-founder of DeepArt and Layer 7, two startup companies, as well as co-initiator of the Alice Initiative. He's maybe most famously known for his work on neural style transfer, which was one of the most cited papers in 2015, and he has won numerous prizes, amongst them the Bernstein Prize for computational neuroscience. One thing that is particularly characterizing for his research is that he's working uniquely at the intersection of computer vision, machine learning, and computational neuroscience. And I'm looking forward to his talk. He will tell us about how we can learn to see like humans. The stage is yours, Matthias.
Thank you very much. It's a great pleasure to be in this special session today. So the overarching topic of my talk is the question, how can we teach machines to see like humans? And Alan Turing has been a great pioneer, putting forth many ideas on how to use machines to mimic the human mind. And in the seminal paper, he summarizes, this seminal paper summarizes many of these ideas. It starts with the Turing test and the universality of discrete state machines. It predicts the growth of memory of computers and estimates that about 10 to the 10 or to 10 to the 15 bits are needed to model the human mind. And then finally, the paper discusses the practical problem of how to fill such a large memory. Turing concludes then that programming will likely not work for that, but it will be important that machines can learn like the human brain. And from a high-level perspective, I like to think about brains as decision-making devices that receive a constant stream of complex variable data and that need to utilize this data for making good decisions. And more specifically, my research largely focuses on vision and on the question, how can we develop visual decision-making machines similar to the brain? And standard approach in the last decade has become to use supervised learning. First, the decision task is defined and presented to thousands of humans. And then after collecting millions of decisions from these humans, machines are drilled to generate the same prescribed responses. The best known example is the ImageNet challenge, where the task is to assign images downloaded from the internet to 1 out of 1,000 different categories. And the standard way in machine learning to evaluate success is to test machines on data that is different from the training data, but drawn from the same data generating mechanism. And the diagram here on the top right shows how this test performance has improved over the last 10 years from 50 to 90%. And so this is really a great success. An important question now is, to what extent high performance on ImageNet also implies that visual decision-making in these networks is similar to the brain? So one way to approach this question is to test what happens if we want to generalize to new conditions or tasks that differ from the previously encountered situations. And I will start with some good news on this. So what got me first excited about deep learning in 2013 was this paper from Trevor Derrick's group, where they showed that the features extracted with deep confidence on ImageNet prove useful for all kinds of other tasks. In a nutshell, what they did is to use the AlexNet as a fixed representation for a variety of benchmarks other than ImageNet, and then only learn a new readout on top of the AlexNet layers. Remarkably, in this way, they were able to achieve new state-of-the-art performance on several benchmarks with very little effort. And I will quickly illustrate this approach. First, to train the deep neural network on ImageNet. So when solving this task with a network, increasingly complex visual features emerge along the hierarchy of layers that also resemble some of the properties that you find in the ventral pathway of the brain. And now you can reuse those as general features also for new tasks. And in the simplest case, this can be done just by retraining the final readout layer. So, and that's exactly what we first explored for the example of image-based saliency. So the MIT benchmark has been the most popular saliency benchmark, where the task is to predict the density of gaze fixations depending on the content of the images. As you can see here in these two examples, the densities of these fixations differ significantly depending on the image content. With the transfer learning trick, we were able to achieve a large jump in the performance on this benchmark, first by using AlexNet features, which pushed the explainable information explained from 1/3 to more than 50%, and subsequently by using BGG90 features, pushed it further to more than 80%. And now recently we have been playing with more recent feature spaces like DenseNet and ResNet, and they're giving the new state of the art. And this can be used for image cropping and selecting the most salient parts of an image. Another example from my group that has been very successful is to exploit transfer learning for flexible key point detection. So this allows to do marker-free key point tracking for any kind of objects with very little labeling effort. And again, the key thing here is that this transfer works very efficiently. Essentially, we found that labeling 100 image frames is enough to track arbitrary key points of all kinds of animals. And so that's why it's now used by many neuroscience labs. And so it's good. So this shows that features learned on the ImageNet, on the image categorization task like ImageNet, can strongly simplify learning of all kinds of other visual decision-making tasks, which means that the inductive bias inherent to deep convolutional nets facilitates some generalization also beyond ImageNet. But high ImageNet performance alone clearly does not imply visual decision-making similar to the brain. I think it is fair to say that the glass is still less than half full and more than half empty, and we are still missing out a lot here. So for example, as you know, it is generally easy to find tiny perturbations to an image that are more or less invisible to humans, but can change the decision of the machine in arbitrary other directions. It is important to note that such adversarial examples are not a bug, but rather striking illustrations that completely different features can be used to solve the same task, the ImageNet task in this case. And there are two related perspective papers that I would like to highlight here, and basically that summarize also the things I'm talking about today. Both discuss the problem that neural networks tend to find solutions to specific tasks or benchmarks that work great, but are substantially different from what humans do and ultimately from the solutions that we are looking for. So the first paper, Engineering a Less Artificial Intelligence, has stronger links to neuroscience, and the second one, Shortcut Learning and Deep Neural Networks, is more related to cognitive science. And so the picture that I have in mind in this perspective is summarized by this diagram that I'm going to introduce. If we want to teach machines a certain behavior, we start with a large set of all possible decision rules, here indicated by this large gray area. And the task is to use both data and inductive priors to identify the intended solution. And then by searching for solutions that have small error on training examples, the set of all possible decision rules is reduced, but still allows for many solutions that do not generalize at all. So by additionally testing machines on unseen test data, we reject all decision rules that we were overfit to the training set. And while this is the standard way of testing in the learning success in machine learning, this is not constraining enough to arrive at the intended solution. Depending on the inductive bias, there might still be large differences in the decision-making behavior when applying to other tests. And in the following, I would like to sketch some systematic differences in the visual decision-making between humans and machines. So most demonstrations either show images that look identical to humans, but fall into completely different categories for machines, or show images that look completely different to humans, but fall into the same category for DNNs. And besides adversarial examples, machines tend to be sensitive to different domains, different backgrounds, or may consider things to be identical if they share some texture properties only, and so on. And so the first example I give is the inductive prior or for texture-based classification. So the high sensitivity of DNNs for texture is a good example for an inductive prior that I believe is important to be changed. About 5 years ago, we realized that DNNs are almost invariant under resynthesis of images as textures. That is, the lodges for different object categories are almost identical, independent of whether you show the original image or a texturized version of it. To test how well ImageNet can be solved based on texture information only, we designed a convolution net with a strong inductive bias for using texture features only. Precisely what we did is to replace most convolutions by one convolutions, such that the receptive fields of the final convolutional layers are still confined to small image patches. So you can think of this as applying the same convnet to all image patches that you can extract from an image and then determine a logic vector over the 1000 ImageNet classes for each patch. And the final classification is then obtained by averaging over all those logic vectors and applying the softmax function. So by design, this network is invariant to the global arrangement of the image content, which is a key property of a texture. And we showed that the restriction of the receptive field size had a relatively small effect on the performance of a ResNet. So for 32 by 32 image patches, it achieves the performance over 86%. And so you can think of this as a back-off feature classifier. As a nice side effect, it is possible to look at the most decisive image patches for the different object classes. While they often make sense, it sometimes reveals also strong dataset biases, such as in the case of the Tench class here. It is often the fingers of the proud fisher which provide the strongest evidence for this class rather than the fish itself. To further investigate the inductive bias for texture, we explicitly investigated how shape and texture cues influence the decision of humans and machines in a Q conflict situation. So in 2015, we developed a method that allows to combine the content of an image with any type of texture. And it is quite remarkable how much human perception tends to disentangle texture information from shape. So this is the method how we can combine the content images missing content images with shape, with texture information. And so you can use this to generate nice artistic images. And if you want to try this out, I encourage you to test out our webpage for this. Now let's go back to probing the inductive prior for textures in CNNs. So Robert Garros used the WordNet hierarchy of ImageNet to study a coarse classification task with 16 high-level classes, such as cat, elephant, bike, bear, bottle, car, clock, etc. And generated images that always combined a shape of one class with the texture of a different class. And subsequently, he recorded both the decisions of humans and machines in response to these images. This is another example. So this diagram here shows the fraction, how often the images were correctly classified based on the shape or based on the texture properties. And as you can see, humans relied almost exclusively on the shape information. In contrast, CNNs are rather biased towards using the texture information. So that's a clear difference. And the difference should also have an effect on out-of-domain testing with unknown noise, as noise typically changes texture information much more than shape in the image. So indeed, if we compare some standard CNNs with humans, you can see that the performance of humans is much more robust against superimposed uniform noise than that of CNNs, as shown here. And clearly, if we would know in advance what type of noise will be applied, then training with this type of noise would allow to generate superhuman performance. However, if we don't know the noise exactly and we train on slightly different types of noise, the performance might easily drop to chance level in the testing conditions. So therefore, we used a different strategy and rather tried to counteract the inductive prior for texture by using data augmentation to randomize the texture information in the ImageNet dataset. The resulting shape ResNet turned out to be significantly more biased towards using shape information rather than texture cues. And like humans, became much more robust against uniform noise, which was not applied during training. So to make our diagram more complete, one can think of out-of-domain testing as one option to further shrink the set of possible solutions and thus facilitate the chance to move closer to the intended solution. I've used the example of how removing the inductive bias for texture cues and how that leads to improved out-of-domain performance with unknown noise. More generally, we can think of different inductive priors to reduce the set of all possible decision rules to different subsets that may turn out to be more or less aligned with our intended solution. A much stronger test whether we have achieved the intended solution is to do counterfactual testing by asking what would be the smallest change in the input that would change the decision in a certain direction. And while the problem to make ImageNet classification robust against such adversarial attacks has been notoriously difficult, I believe that generative modeling plays an important role in imposing more powerful inductive biases. And I would like to highlight some successes on MNIST that we achieved with generative modeling. So we have basically trained a generative model for each digit class and achieved 99% performance on MNIST by letting these generative models compete in explaining the input. And while for a long time also for MNIST adversarial examples just looked like the original image or slightly noise versions of it, we find for our analysis by synthesis model that we start seeing perturbations that make sense to human observers. Here on the right-hand side, you can see a few examples of images that were obtained by doing gradient descent towards the decision boundary, such that each image belongs with equal probability to two different classes. In fact, the uncertainty of the machine resembles the perception of humans who qualitatively see the same ambiguity in these images. So in the top digit, you can see either a 6 or a 0, and that's also what the machine assumes. And then next one, a 2 or a 1, then a 7 or a 2, 3 or 7, and finally 4 or 9. So a recent study by a different group has studied this in much more systematic fashion. They generated controversial stimuli between all pairs of models, such that, for example, one model is sure to classify the controversial image as a 7, whereas the other model is sure to classify the same image as a 3. And on the right, you see how such controversial images look for all pairwise combinations of a selection of 9 different models. And in addition, they also showed these controversial stimuli to human observers to determine which models agree the most with human decision-making. And it turns out that our analysis by synthesis model exhibited the best alignment with human decision-making. In the example on the right, one can assess this by the fact that the images in the bottom row all look like a 7 to us. whereas the images in the rightmost column look like trees to us. So I consider this success a nice proof of principle that generative modeling might be quite useful if we want to align the visual inductive priors of machines with that of humans. However, it is clear that it is still quite a leap to demonstrate the same thing also for nature images. In particular, I believe that we will still need to make significant progress in developing the right type of generative models for nature scenes. One important aspect is that generative models should be object-centric with the notion of occlusion that we studied in this recent paper here. Another aspect is that these generative models should also have a notion of the compositionality across the scale hierarchy. These are aspects that I'm very excited about, but we are just at the beginning to explore. So, complementary to counterfactual testing, which looks at small changes with large effect, the last work I would like to mention is related to looking at large input changes with small effect. In particular, we started to explore how invertible neural networks might provide an opportunity to study the invariance manifold that determines how a neural network generalizes. So in many cases, the input of a neural network is much higher dimensional than its output, and more information about the input gets lost at downstream layers. Understanding what information gets lost may help to understand how networks generalize, as it is directly related to the invariance of the network. So invertible neural networks are designed that at any layer, the original input can be reconstructed, and we will call all variables that are not trained to match the labels during supervised training as the nuisance variables. So that's shown here. Yes, usually in standard neural networks, the nuisance part is thrown away, and in invertible neural networks, you can also parameterize these invariance manifold of the neural network. And so for MNIST, the input dimensionality is 784 dimensions, and based on the one-hot encoding of the 10 classes, the signal space is 10-dimensional, and the nuisance space is 784 minus 10, so it's 774 dimensional. Similarly, for ImageNet, the signal space is 1,000 dimensional, and the nuisance space is roughly 150,000 dimensional. So we can now use these invertible networks to easily synthesize images that recombine signal nuisance information of different images. To this end, we can combine the signal output of one image with the nuisance output of another image, and then determine the corresponding pre-image. So here you see these two columns, both for ImageNet and for MNIST, and we take the signal space of the left column and the nuisance space of the right column, and then compute the pre-image in order to determine, in order to generate a new image with exactly the same logits, exactly the same activations in the signal space as the signal image. But as you can see, the information in the image is basically identical to the image from which we took the nuisance information, which is maybe not too surprising given that the nuisance space is much higher dimensional than the signal space, but it also shows that, the perceptually relevant information, perceptually relevant to humans, is here rather encoded in the nuisance space. So this finding motivated us to modify the cross-entropy training by an additional term in the objective function that tries to make the nuisance space as invariant as possible with respect to the labels. And it turned out that this modification successfully changed the decision-making behavior of the network. For comparison, I first show here again some examples of pre-images that were generated with the network trained with standard cross-entropy training. using the signal information from the images in the top row and the nuisance information taken from the images at the bottom row. And as you can see, the the generated pre-images look much more similar to the images in the bottom row than to the ones in the top row. Now, if we add this minimization of image information between the nuisance space and the labels, we get a different neural network. And if we look at the pre-images of this neural network, the pre-images look much more similar to the signal space, to the images from which we took the signal space. So again, this is only a proof of principle on MNIST, but I believe that studying how we can actively encode shape invariances in neural networks is crucial, and also a great opportunity for the design of better inductive priors. So I would like to summarize now. In this talk, I try to provide a common perspective on a range of different studies we pursued in the lab that all aim at a better understanding of generalization and shaping inductive biases to make visual decision-making in machines more similar to human vision. I find it helpful to think of both data and inductive priors as constraints that we want to combine to shrink the set of possible decision rules towards the intended solution as effectively as possible. And in the future, I think that inductive priors facilitating object-centric representations and compositionality along the scale hierarchy will play an important role in improving automatic image understanding under general conditions. That's my talk. Thanks for your attention.
Super. Thank you very much, Matthias. Yeah, if you have questions, please ask them on Discord. Maybe let me start with one. So for this shape and texture, like for this results on the texture bias of neural networks. So one question is like if you use these images generated using style transfer for training, how much do you? I guess you pay something in terms of accuracy. So how much do you pay if you pay something?
Well, you actually, so we train on both, or if you train on both the original and the stylized images, then you don't pay accuracy.
Okay, so you can maintain the same accuracy level while being more robust. I see, that's great. And do you have any intuition of like what is the underlying cause? Like what would you need to change in order to create networks that may not need these additional inputs for training, but that have incorporated these assumptions more directly into the architecture, for instance? Do you have any thoughts on this?
Yeah, I mean, that's, I guess, what I mentioned towards the end. So I think if you think of the pooling and the different layers in a hierarchy of a deep network, then all these intermediate, the representations in these intermediate layers, they don't really relate to parts of objects in the physical world, right? So, and parts usually reflect also the properties how objects can be combined. And so I think one intuition I have is it would be great to have a deep neural network where the hierarchy is not only, which is both a scale hierarchy and a hierarchy of accumulating nonlinearities, if that also allows to more explicitly represent parts of objects at the intermediate layers that are then composed on the next level and uses some pooling or some combination that is more tied to the physical properties. Mm-hmm. I'm not sure whether that's possible in this image-centric fashion, where or retina-centered coordinate system, as neuroscientists would say, but it might need more like attention mechanisms that segment out individual objects. And you have, by this figure ground segregation, you also disentangle the causally relevant information for an object identity from the background, which shouldn't really determine what the object is, right? So the grass shouldn't determine whether you have a cow or not. It can encourage the network to expect a cow, but it shouldn't decide this. Mm. And then it might also help to make this, pooling across scale more feasible.
Mm-hmm. So there's two questions also in the chat, actually getting more and more now. So let's see. So the first one is a little bit related, I guess, to what we just discussed. The question is, how many such constraints, referring to the last slide, I guess, do you think one would need to push models in the human direction?
Yeah, so I think that's a very good question. So when I started to think more about this picture, then you start thinking about what would be also an optimal combination of out-of-domain testing, right? So at the moment, this is kind of ad hoc. We obviously want neural networks to be robust against all kinds of sensor noise and maybe certain domain shifts that we can think of, but it would be really cool if we would come up with some theoretical insights, what combination of out-of-domain tests would be most effective to constrain the solution. And so I don't have answers yet, but I think the thinking about this question is interesting, and I would like to do more research in that direction. Yeah.
Another question was why, thank you for the interesting talk, why is it not yet possible to imitate the natural optical neural path with artificial neural networks? Is there not discovery in the neuroscientific area to make this possible?
So there was one, is the question why we are not able to incorporate more knowledge from neuroscience in the networks?
I think it was rather why we are not able to imitate the optical neural path. So why can't artificial neural networks not exactly imitate the optical neural pathway? For I guess it's possible, right?
Right. So I mean, one has to be obviously clear about what it means to do that. I think one active area of research in neuroscience is to predict neural responses in these different areas. So like in the retina, there are different cell types, B1, B2, and so on. So one pathway that is very much studied is this ventral pathway that also gave inspiration to convolutional neural networks and shares properties like this retinotopy, that you have the same type of computations everywhere in the visual field. But for instance, you don't have weight sharing, so there must be some learning mechanisms that impose that. And it's not trivial. So we didn't have an ImageNet moment yet on predicting the neural responses in the brain. So there's deep learning helps. But it's also, you rather want to understand the feature, like the computational features than one particular neuron, right? So you want to group neurons into classes of cell types. And there's progress there, but it's also not solved yet. That's one thing. And the other thing is obviously from a cognitive perspective, we not only have this ventral stream that very much looks like a convolutional neural network, but we also have a dorsal stream and a lot of other neurons in the brain that interact. And for the cognitive perception, I think this is quite relevant. For instance, you can imagine, or I like to think of the dorsal stream as a mechanism that segments objects and does some object-centric computations combined with a more retina-centric ventral stream.
Mm-hmm. Cool, thanks. I think we have to stop here now. There's one more question on the Discord channel on Gestalt principles and how they could be useful in this context. If you have a few minutes, maybe you can quickly check and answer in Discord directly. So thanks a lot, Matthias,
Thank you.
the talk. And let's now, maybe you can disable your screen and let's move on to Sabine Systrunk. You can already share. Sabine Systrunk leads the Image and Visual Representation Lab in the School of Computer and Communication Sciences at EPFL since 1999. And she's broadly interested in computational photography, computer vision, machine learning,